Okay, so here's problem number 16, another thin film interference problem. So if you haven't already, pause the video, draw out the sketch of the light reflecting off the top edge and the bottom edge of the film, go through the flips, and identify what equation you're going to use. Then come back to the video to make sure you're on the right track. So I first draw the media, and I'm going to identify it starts in air, and then there's going to be the thin film of the non-reflective coating, and then there's going to be the glass onto which the thin film is applied. And we're going to show the light coming in here from the air. Now, it is white light, so I guess maybe I could have used maybe black to indicate white light. So here we're just using red to make it a little more colorful. And remember, we want to say it's going to hit this top boundary of the film, so we'll call that boundary 1. And every time a wave hits the boundary, some of the energy gets reflected, some of the energy gets transmitted. The reflection is real easy. It's obviously going to reflect at equal angles on the other side. For the refraction, for the transmission, we say, well, what's the light doing? It's going from the air into the coating. We see the index of refraction increases, which means that the light slows down, which means it's going to bend towards the normal. So it refracts towards the normal a little bit. And then, of course, it hits the second boundary, the bottom edge of the film, between the film and the glass. We'll call that boundary 2. Again, some of the light gets reflected, some of it gets transmitted or refracted. And so here's the reflection, easy. What about for the refraction? Well, it's going from the coating into the glass, and you see the index increases again, which means it's going to slow down, which means it's going to bend towards the normal again. More importantly, though, is this reflected ray, because the reflected ray now goes from the coating back into the air, where it's going to speed up, bending away from the normal, and so it's going to come out parallel to the original reflected ray. This left-hand reflected ray reflected off of boundary 1, so we'll call that reflection 1. This one reflected off boundary 2, so we'll call it reflection 2. And remember, even though right now we're looking at the light going at all these different angles, we're going to pretend that this incident ray is hitting dead on onto the coating, and so the reflection is going to come right back at it, and the reflection from the bottom edge is also going to come right back at it. So these two reflections are going to overlap and interfere. What sort of interference will they produce? Well, here's where we go through the flips. So we think about the flips at boundary 1 and boundary 2. At boundary 1, the light is slowing down. That's mimicking a fixed end reflection. That's where it does flip over. At boundary 2, going from the coating into the glass, it again slows down, which means again it's going to flip. So you're always thinking about what does the light do as it enters a new medium, and what does that cause to happen to the reflection. Remember, anytime the light slows down when it goes into the new medium, the reflection back into the first medium flips over. So, for example, if it came in here as a crest, reflection 1 would come out as a trough. It's still a crest going in here to boundary 2, so if it comes in as a crest, it's going to flip over as a trough there, and so they're both flipped over, they're back in phase with each other. What sort of interference does that make? That makes constructive interference. They're back in phase with each other. All right, so after all that prep work, now we finally look to see what the problem is asking us to do. So we're looking for which wavelengths are destructively reflected. From the flips, they're constructively interfering. So which equation should we be using, the keep or the change? Hopefully you recognize we're using this equation because right now they're constructively interfering. We don't want them to be constructively interfering. We want them to be destructively interfering, and so we want to change it, and that's where it's going to be off by the half wavelength or 3/2 or 5/2. Okay, so let's make sure we're understanding what the terms are in this equation. T, remember, is the thickness of the film. That's going to be the 0.106 micrometers. Lambda naught, that's the wavelength in air. That's what we're going to be looking for to see which wavelengths are destructively reflected between 400 and 700 nanometers. M is the order. We're going to get to that in a second, but really it's just an integer telling you how many half wavelengths it's going to be off by. And then N, something maybe we didn't emphasize as much in class, N is going to be the index of refraction of the film. Remember, this term here, lambda naught over N, is really representing the wavelength in the film. As the light goes from one medium into another, the wavelength will change, and we are all considering here, we're only considering the wavelength in the film. It's all about the film, the thickness of the film, the wavelength in the film, and so in this case, this N is going to be the 1.23, the index of refraction of the film. So first thing you want to do is, of course, rearrange this for lambda naught, so go ahead and do the algebra for that. So it should look like this, 2nt over the quantity m plus 1/2. The question is, what's m going to be? Well, you don't know what m is going to be. Really, what you have to do is just sort of play around with it until you find a wavelength, or possibly more than one wavelength, that fits the bill in our visible color spectrum. So just arbitrarily, let's start with m equals 0. So plug in m equals 0, put all your numbers in there, and let's find the wavelength. And since we want to see if it's in the visible spectrum, which is between 400 and 700 nanometers, you want to make sure that your end answer is in nanometers as well, so you can make easy comparisons. Remember, this thickness is in micrometers, that's 10 to the negative 6th meters. And so we put it all together, we should be getting a wavelength of 522 nanometers, which would be 5.22 times 10 to the negative 7th meters. A nanometer is 10 to the negative 9th meters. When you do the conversion, you get 522 nanometers. So we say, is this in the visible spectrum? Sure, it's kind of right in the middle between 400 and 700, so that's good. That's going to be one of the wavelengths, but we need to continue to see if there are more. So what do? We go up to m equals 1. So do the same thing. We put your numbers in for m equals 1, you should find 174 nanometers, or 1.74 times 10 to the negative 7th meters. Is this in the visible spectrum? No, it's clearly too small. Should we continue? Well, if we continue, we're just going to make this wavelength even smaller. It's even more out of range, so we're done. We don't want to go past that. We can see the only wavelength that's going to be destructively reflected in this case is the 522 nanometers. Okay, so what was the whole point of this? Why are we putting this non-reflective coating? What's going on here? Well, notice that the 522 nanometers is pretty much smack dab in the middle of our visible color spectrum. Here's the idea. People who wear glasses have this problem that when light is incident on it, the coating, the lens itself acts as a mirror, and so some of the light gets reflected. So you want to put a coating on there that's going to cancel out those reflections, a non-reflective coating. In this particular case, it seems like there's only one wavelength that's going to be destroyed. Well, here's the deal, is that while the coating is 0.106 micrometers thick, it's very unlikely it's going to be a consistent 0.106 micrometers thick, and so there's going to be some natural changes and variations in the thickness. And with these minor changes, it's going to cancel out other wavelengths that are also near 522. And so with all the different variations of the thicknesses, it's very likely it's going to cancel out a whole bunch of these wavelengths. And so if light is incident on this lens, very few of those wavelengths are going to be reflected. So anyone who's ever taken, for example, school pictures wearing their glasses, when they have the flash from the camera there, sometimes you get the pictures developed and you see that there is a reflection on your lenses. And so if you pay a little bit extra money and get this non-reflective coating on it, that eliminates those reflections, and your school pictures look that much better.